Hello, in this section 2.4, we will discuss dimensionality reduction. So a very common issue with dimensionality, having many dimensions, is called curse of dimensionality. As the number of features or dimensions grows, the amount of data that you need grows exponentially as well. So if you have more features, that means you have more columns in your data frame, you'll need a lot more rows, right, data points to counter the sparsity that you get from the growth of the features. So that's why we want to do our best to reduce the features. And then PCA, principal component analysis, is the number one technique that people use in data science to accomplish that, to really reduce the number of features. And then the implementation is fairly easy. As you can see, that you can just do it within 4 lines of code. But behind the scene, PCA it's about, think of PCA as a compressor, right? So say you start having, so your features originally are you have 100 features, and you'll try to compress them so that in the end you'll get 10 new features. But the 10 new features, they are made up with some percentage of the original feature 1, some percentage of original feature 2, some percentage of original feature 3, and so forth. So what you're losing there is that you cannot interpret the features like before, right? If you just use original features as we've been using this data set, number of bedrooms is pretty easy to understand what that means. Or number of, bathrooms or a square footage, it's very easy to interpret. However, if you're saying 20% bathroom, 30% bedroom, the rest is coming from square footage. That's your new feature, right? New feature 1, right? So that is not so easy to understand, right? What does it mean? So that's what you're losing. But the flip side is that you can really avoid, right, this curse of dimensionality and really compress your feature space. So let's get started, right? So like I said, implementation is fairly easy. You can just do from sklearn decomposition. So this is another sub module of sklearn, import PCA, principal component analysis. And this is where you can initialize, right, your PCA. What you're saying is that I want 4 components. You wouldn't know this from the beginning. Sometimes you have to grid search, or other times you can use the elbow approach, right, to see where you should stop, right? Definitely you will have the new feature set should be lower than the original feature set, because that's what we're doing PCA. However, where to stop is tricky. You will need to sometimes do a lot of trials and errors. Other times you can look at elbows, plotting to see what is the drop in the explained variance by adding a new feature, right? So that's where you can determine if 4 is a good number, or 5 is a good number, 10 is a good number. So now we have this PCA, we can do PCA.fit transform. So remember our X, right? So our X is, we have 7 features, right? We'll have 7 features, and then all these, rows, and then we can look at the shape of it, right? So we have 15,007, right? So now we are going to use this PCA to fit transform it. We can do it all at once. So fit it and transform our X. And then I call this X transform as, the transformed X as X transform. And then let's look at X transformed shape, right? Okay, let's look at the shape. Now you can see I have the same number of rows. However, the number of columns now reduced from 7 to 4, right? So because I define the PCA, right, that I want to use to fit and transform as 4. It has 4 components, right? We call it eigenvectors, right? It has 4 components. And then here is a very useful function. So PCA.components will tell you the components, right? So look at the components. We can actually look at the shape, right? The shape of that is 4 by 7. What that means is we have 4 components, and each component is made up by the original 7 components, right? So that's what that means. So let's look at the first component, right? This component means like the new feature, right? After we do the transformation. So let's look at this. So now we have 1, 2, 3, 4, 5, 6, 7. So we have 7 numbers in here for this new feature that we got, right? This new component that we got. It just means that this is kind of like the weight that we assign to the original feature 1, which we know is the bedroom, right? And this is the weight that we assign to original feature 2, 3, 4, 5, 6, 7. So these 7 features are contributing to our new feature, right, or component. And then you can see for this one, the highest, the one that's contributing the most is really the last one. The last one, I do believe the last one is prior, right? It's a prior serial amount. So you can pretty much say that the first component, is dominated by prior serial amount, right? So let's then use this new, X transform, right? And then we're going to fit the same model, right? We have our Y, which is, where our Y is just the estimated value. And then we're going to use linear regression because what we're trying to predict is a numerical value, and then we need to initialize it like this, right? We have imported linear regression already, and then remember what we can do is we have to do train test split, right? And then now we want to use is the transformed one, not just X, right? We want to use the transformed X, and then Y is just the same, right? And now we want to say train X test, and then Y train, and then Y test, right? So this is equal to that. So now we can say LG dot fit of this X train, right? And then Y train, right? So we're going to fit it, right? And then LG dot score of our X test, and then Y test, right? So it's 70%, right? So compared to our original linear regression, let me take a look at what we got without the transformation, the PCA transformation. Remember the score, it was, it was almost the same, right? I think what we got is slightly better, right? This is the score for linear regression is actually R squared, right? So it's slightly better. It's not a dramatic improve. Well, actually, it's worse. My apologies. It's actually worse. So this really tells you that you don't need to you shouldn't be doing the PCA because, 7 features is not really a lot of features to start with, right? So we didn't have to, but this is to really show you how you can actually do PCA. But on the other hand, so what if we want to just, remember DF was our original feature data set. So it has a lot of, columns. What if we want to use everything in here, right? What if we want to use pretty much, everything except for the target variables, right? So there we can use PCA more effectively because we have more features to start with, then apply PCA and transform our feature matrix and then fit into a model. So, but this is to tell you really quickly how you can use PCA, right? How you can apply PCA, how you can use what you transform through PCA and fit a model. That's it. Hello, in this section 2.5, we're going to continue discussing PCA, dimensionality reduction technique. So what is PCA, right? So in our previous section, we have talked about how to implement PCA using a sklearns library, right? So PCA under the hood is a complexity reduction technique that tries to reduce the set of variables down to a smaller set of variables or features. Say you start from 100 features, you want to reduce it to 10 features, right? So in a conceptual level, right, if you look at this diagram, you have one set A and set B, right? And then think of these circles with different colors or different features. So the first example will be you have one PCA, one component after fitting a PCA, right? Because PCA is to explain the shared variance in the middle, right? So you can see that you'll lose some information, right? like in here, right? That's not being covered in this area. And then in set B, you're gonna have possibly you'll have two components. One is in here, right? And the other is in here. And then whatever you have outside will be lost. So PCA is not to explain all the variance from your original feature set, right? You will lose some variance, but it can be worth it, right? So then why do we need PCA? Under the hood, it's really just about curse of dimensionality, right? So here's one example. You can actually see in 1D, if you only need to search for, let's say, 5 boxes. But in 2D, if you want to search through this entire surface, you have to search through like 5 times 5, like 25 boxes, right? In 3D, it's going to be 5 times 5 times 5. So really, if you have, with high dimensional data, we simply cannot comprehensively sample all of the possible combinations, right? So that's what the definition of curse of dimensionality. And therefore, we want to use PCA to reduce the feature set, right? Then let's take a look at one example. So we can actually use this data set that's called ESS data. So it's pretty much a happiness score data based on the survey. So you can actually see I got this CSV right from Kaggle, and then this is the head of this data frame. You can actually see country, and then ID and year, and then this is like how long TV, I think, and then this is like the trust, right? Trust level or trust score. And then this is the fairness score. And you can actually see it's like the happiness score, right? So let's just take a look at, we can just pick two countries. One is Czech and the other is, I think, Switzerland. So we'll just say pick 2 countries like this. And then we want to plot, right, the trust score versus fairness score. So we have 2 features that we want to just do a scatter plot of. And you can actually see that there's like a blob in the middle, right? Almost like a linear, sort of like a linear correlation, right? So what we can do, right, with this PCA is really to find out a new axis. Think of PCA is about bringing your axis towards data, closer to data, right? So what can we do, right? What this information is, we can actually draw this line. You can see this red line, which will become our new x-axis, right? Not like this. This was our original x, original y, but instead of using the original x and y, we want to use this as our x. You can see that this line can somewhat explain 2 features, not all of them, because you'll lose some variance in here, right? But it is the best representation. Consider this plot, right? So this line, right, you can think of is one of the components that we can use after PCA, right? So the math behind PCA is really just, we have to start from covariance matrix, right? So covariance matrix is pretty much, we all know what variance is, right? So this is a definition of variance, and covariance is really just about, it's the product of difference of each variable values and its means divided by the sample size. So with this, right, so we can actually create the covariance matrix like this, right, based on what we had before for those for these 4 features, right? TV, TLTs. This is, I think, how long you'll watch TV, and then trust score, and then fairness score, and then this is if people are helpful or not. I think that's the definition of this feature. But you can actually see the covariance matrix, the diagonal ones are all 1, right? Because it's to itself, therefore it's going to be always 1. But these are pretty much like the covariance between the second feature and then the first feature, right? So trust versus TV, TOT. And you can see that it's symmetric, right? This number is the same as this number. So this is our covariance matrix, right? So what eigenvectors are, right? So eigenvector is really just a directional aspect of the components, right? So it's this red line, right? It's this red line, but it's going to be the unit vector, and that means the length is going to be always 1, right? It is going to tell you the directional aspect of the component. So really, eigenvectors are chosen to be orthogonal, right? So that is to have really a correlation of 0 with one another, right? So I remember our original x, y. Typically, I mean, x and y, they're orthogonal, right? X and y. So if we choose the first eigenvector to be like this, right? First component to be like this with this direction, then the second eigenvector should be perpendicular to this one. So it's going to actually go like this, right? Like vertical, right? Like this. So that's the only rule that you have to follow. And then first, this vector is found to minimize really the distance, right, between the vector and the data points, right? And then the vector is the first component, just like the red line we had. And next, the second vector is found that also minimizes the distance between that vector and the data points, right? The second vector must be perpendicular to the first one, right? In one of the n dimensions of the space. So we don't know which one because this is only the 2D plot. So you wouldn't know which dimension, but the rule is that it has to be perpendicular to the first one in one of, right, only one of the n dimensional space, right? So, and then we just continue this procedure until there are like, you know, how many or n vectors, right? So then what's eigenvalue? Right? So eigenvalues represent the length of the eigenvectors. So really, it's about the proportion, right, of total variance explained by a component, right? So the total variance is always equal to the number of features, variables in the PCA, right? So if you have 100 features, the total variance is going to be 100. So therefore, eigenvalue of 1 really just means that the component explains the same amount of variance as just one of the original feature, right, or variable, right? So eigenvector value greater than 1 is kind of like the general rule, right? It's desirable because what you want to do is think of PCA as like a compressor that it wants to compress your feature space into more dense feature space, right? So therefore, you want to have one, right, eigenvector or one component explaining more than just one, the variance that you get from one of the original features. You want to say, you know, this one component, right, after PCA can explain, right, more than the variance that that you get from, you know, several features in your original feature set. So that's kind of like the general rule, right? And then yeah, it doesn't mean that it's always, you know, there is a hard cutoff, but typically you'll want to say eigenvalue should be greater than 1, right? If it's below than 1, then maybe that's not the component that you want to include, right? So let's then take a look at, you know, the eigenvalues and eigenvectors, right, from our data set. So you can actually see we have, remember, originally we had like 4 features, right? So, and then we want to fit, you know, use PCA to transform these feature space into something smaller. So if you look at this like 1, 2, 3, 4, we can actually do it up to 4, right? So, but then it doesn't really make sense if you had, say, 4 features and then after PCA you still end up with 4 features, right? Typically you'll want to, you'll want to reduce your feature set. Therefore, the features that you get after PCA should be less than your original features, right? So I would say this, the cutoff looking at this, right? It's just 1. I just want to have, you know, the first eigenvector and then eigenvector with the value of this as my first component, right? So, and then the contribution, you can see that, right? These will add up to 1, right? So you can see that the contribution from the first feature, right, which is TOT, is actually negative, right? 30% negative from the first one, and then 55% from the second, 57% from the third, and last one gets 50. So if you do this, it should add up to 1, I believe. So, and then, so you can actually see, so then like, no, actually, this should add up to 2.21, so the eigenvalues. So you can actually see from eigenvector 2, the eigenvalue is below 1, right? That's kind of our general rule in saying that, okay, if it's below 1, that means it's actually doing worse than one of the original features can do, right, in terms of the variance explained, so I don't want to include this, right? So this is where I can like just draw a line and say, okay, I only need 1. So meaning like I start with 4 features, I end up with 1 component, right, after PCA. So, I mean, how many components is debatable. You can actually look at things, you know, like this, right, eigenvalue, that's a good one. Or there is another one that's like almost looking at the plot, right, like the elbow, right? We'll call this like the elbow approach. You can actually cut it in here or there, but I will say because we have this another like general rule of only including components with eigenvalue greater than 1, so therefore I'll say, yeah, 1 is a good place to, you know, to cut, right? So, yeah, so that's it. So remember, these numbers will add up to the eigenvalue, right? Pretty much it says, what is the split between the original features? We have 4 features that will add up to the eigenvalue, right, for this new component, for this component, right? So, and this is to say, I have, with this one component, I can explain, I can actually have the variance, right, that the original 2.21 features can really bring, right, can have. So it's more condensed. With one feature, with one component, you can actually explain, right? You can actually have the effect or the predictive power of 2.21 components or features, right, from your original feature set. So, and then under the hood, really, PCA is a series of linear transformations, right, applied to a data frame that you can reduce your features, right, to really avoid curse of dimensionality. As we have discussed, curse of dimensionality is really about having higher dimensional space. It's really hard for you to search through, right, of this high dimension space because the power typically is, you know, n to the power of, if you split your one dimension into 5 boxes, you're going to have 5 to the power of n, right? So n is your number of features or number of dimensions. So therefore, you can see that this number can explode fairly quickly, right? So that's why we want to use PCA. And then there are other reasons, right? As to like, typically when you have more features, the features can definitely the models tend to overfit, right? So with fewer features, it's you can avoid overfitting, and definitely computationally speaking, if you have less features, it's the runtime is going to be shorter, right? So there are many benefits, but the flip side of that is really you'll lose some variance. Remember, with PCA, with this transformation, you're not going to have all of the variance, right, from your original feature set. You'll lose something, like, you know, what we've shown here, right? Like if you just use this common area in the middle, right, as your final component, then whatever outside of this, right, will be lost, or, you know, whatever outside of this will be lost, right? So that is the flip side, right? But so therefore, like, it definitely takes many iterations for you to find out the sweet spot, right? Like how many components you want to include, where do you stop? So a lot of time you can grid search, right? PCA typically, as we explained last time, the implementation is fairly easy. You can just, you know, write a for loop to say, I want to search through the best number of components, right, that I need to have, say from 5 to 10, right? I want to start from 5 components to 6 components and all the way to 10 components. And then wrap that around, say, one specific model, right? Either say logistic regression or linear regression. And then you want to say, okay, so for this combination, right, PCA with 5 components and then linear regression will give me the best results, right? Then I can say, I can conclude that, okay, 5 is the best PCA, right, in terms of number of components. So definitely there are many ways of doing this, but it definitely takes a lot of iterations to find out, the best components. You wouldn't know from the beginning. You can actually look at all these, the elbow plots, or look at eigenvalues to determine how many components, right, that you want to include. But this is pretty much it. PCA is definitely very important, and then I think you'll be using this technique very, very often. Thank you.